6.5, operations with radical expressions. Next slide. Product property of radicals. This is a fancy way of saying that, this is the fancy talk for talking about how we break down radicals with a factor tree.
Take a picture?
Okay, no, don't even. Okay?
Oh.
All you really need to put on this slide is factor trees. Alright, because that's what this means. That's what this is talking about. If you look here at the example down here, let me get my arrow to the right side. There we go. See how it says here rad 2 times rad 8 gives you rad 16, right? See that? So it's kind of a twofold property. It lets you multiply the insides radicals together. Okay, so there's one. But the other thing it lets you do is it also lets you split them up. Okay, see that? Because it's a two-way street. You can go from here to there, or you can go from there to there. So this property is important, but you already know how to do it. You know, you guys know how to factor tree stuff. That's not a big deal. Okay? You guys know how to multiply numbers. That ain't a big deal. So you guys know how to do these things. All right? So it is an important property to know because we use it a lot, but as far as knowing the actual name of it, you know. I'm more so care that you guys can do things with it instead of just naming properties, alright? So essentially what we're going to do is, remember, we got to factor tree a lot of different stuff, alright? Before we do that though, this is like, I don't want to say the gospel of the radicals, but it's essentially the gospel of the radicals. It's your 4 bullets. It's what you need to make sure that happens to everything. Alright, a radical expression is in simplified form when the following conditions are met. The first one is the index is as small as possible. It's almost always the case. Alright, we ain't going to get into the questions where that's not the case. Okay, the radicand, this one's important. It's fancy words, but it's important. The radicand contains no factors other than 1 that are nth powers of an integer or polynomial. Basically what that one is saying is if there is something that can be factor treed out of the radical, you need to factor tree it out of the radical. Right? Makes sense? Like if you have the square root of 48 and you divide it by 2 and get 24 and 2 and get 12 and you leave it, and you say the square root of 48 is 2 square root of 12, that's not correct. Why not? What's 12 got in it? 6 and 2, or say the other one. So 4 and 3. And 4 has a 2 and 2.
3 and 2.
Okay. So you see what it's, either way, no matter how you get there, you still get there, right? So 2 rad 12 is not correct because it can be simplified further to 4 rad 3. That's what this one here is talking about, all right? If it has a factor inside of it, it needs to be factored out. So basically factor tree that stuff. It's 4 rad 3. Okay. The last, and then that's the one we're going to work with mostly today, okay? These last 2 bullets, the radicand contains no fractions and no radicals appear in a denominator. This is more so for Monday. Okay, this is going to be more so Monday's lesson. Monday's half of this section. Today we're going to mostly factor tree and then do some adding and subtracting and some multiplying. Number 1, the square root of 32x to the 8th. FTTS. Factor tree that stuff. So you just go through and start factor treeing. 32. Factor trees 2 and 16. And 16 goes. See, no, your perfect square. 16 goes 4 and 4. All right. That way you get it when you got them and you're done. right? Save yourself some time. Okay, so know your perfect squares, know your perfect cubes. So there's a pair of 4s. All right, now take these part by part, okay? So I always kind of do, what I do is this. I go out, I make an out column and an in column off to the side. Okay? Outside the radical, inside the radical. Because these aren't perfect anymore, right? 6.4, they were perfect. 6.5, they're not. So these will have some things left inside the radical. So we have to make sure that we keep them organized as to what is inside, what is outside. Okay? So outside comes your pairs, and they go as 1. So outside we have how many 4s? 1. Anything not paired up is inside. So 2. Okay? Now that you're done with your 32, now you go to your x to the 8th. Factor tree it. Okay, if you have to write it off separate like this, that's fine. Okay, you can still use your same divide trick on that one, or you can factor tree it literally. Yeah, but you go x to the 4th, x to the 4th. There's your pair of x's to the 4th, so they come out. Oh. What's x to the 4th times x to the 4th? Add. Yep. Okay. Okay, and once you do that to everything, now you write your actual answers. So your outside is 4 x to the 4th. Inside a square root of 2. Okay, now, most important thing you need to realize is what your index is. And this one, your index is 4. So instead of groups of 2, we need groups of 4. All right, so same way. Make an in column, or here, first out column first. Outside the rad, inside the rad. Factor tree 16. 4 and 4. And each 4 goes 2 and 2. So there's a group of 4 2s. They come out as 1 2. Okay. So 16's done. Okay. So now you have a to the 24th. Same way, you can do 24 divided by 4, which gives you a to the 6. Whoops, that's 9. A to the 6. Just add them all up, right? 6, 12, 18, 24. Remember, that's multiplying on your leaves for your trees. Okay? And I'm doing this way to show you here first in a sec, okay? So just hang tight with me here, okay? So you have 4a to the 4th, or a to the 6th. Everybody see that? They all come out as 1a to the 6th. Okay, so we finished 16. We did a to the 24th. What's left? B to the 13th. Okay? All right. Now, I'm going to factor tree b to the 13th. Okay? All right. So, there's multiple ways you can factor tree b to the 13th. You can make a factor tree of 13 b's. Right? Okay, you can do that because they all add up back to 13. There's a couple other different ways you can go. All right? But I know my index is what? 4. Okay? So what I'm going to do is this. I'm going to make it so that I'm going to divide 13 by 4, which gives me what? What's 13 divided by 4? 3 something, right? It's 3 something. Okay? It's 3 something. So I know from that can have b to the 3rd, b to the 3rd, b to the third, b to the third, right? How many b's is that? Total. Total, it's how many?
4, 5,
12. It's 12, right? It's 12 of them. So how many am I missing from 13? 1. Here's why that matters. How many do I need in my group? 4 in a group, index of 4. There's my 4 b cubes. Everybody see that? What's left over?
Oh, it's B.
This b, which is left inside. Whoops, that's a terrible b. Let's try that again. Much better. Not really, but still. Okay. Basically, whenever your variables are not perfect, you divide it by the index still, that's fine. That whole number, whatever that whole number is what's going to be coming out. Okay? So 13 divided by 4 gives you 3.25. Okay? That 3 is the index. Or not the index, sorry, the exponent that comes out. You just have to figure out how many b's you have left over. Okay? 3 times 4 gives you 12, right? There's 12 b's written right here. 3, 6, 9, 12. You had 13 total, so you have 1 left over. Everybody see that? Okay. Questions?
So it's 2a to the 6b to the third.
Yeah, I should probably write that down, huh? That would help, wouldn't it? Yes, Mr. Mormon, it sure would. 2a to the 6th, b to the 3rd. Okay, most important thing. What type of root is this on this one? It's a 4th root. So your answer is a 4th root. Yes. Every single time your index is not 2, that index never changes. All right, for you guys' purposes, and for most people's purposes, that index does not change. Okay, so if you start with a 4th root and you have something left over inside, you write it as a 4th root. Okay, I do look at that. I will take off points if you don't. It's very important. There's a drastic difference between a 4th root and a square root. Big difference. Huh? Questions up here? Everybody good? Garcia.
So if like A was like 25, we would do the same thing as A?
Yes, sir.
Add it to
And this side. Yep. Or if it was 26, let's say it was 26, you would still break up it into a to the 6, but then you'd have 2 a's inside.
Would we have to add the number thing like we did before?
Mm-hmm. Okay. Because in your final answer, inside on your variables at least, the inside variable should never have an exponent that's bigger than your index. Okay? Because if there's, like, say there was 4 b's left inside, you have a 4th root, so you can make another group of 4 out of there. Okay? So if you have that, then you know something's funky. All right? Anyway. All right, so number 3, we're going to factor tree 12, which goes 4 and 3, and 4 goes 2 and 2, like that. All right, so that pair of 2's comes out. The 3 stays in. Okay. Now, see the 6, you need pairs, so how can I write that? You can go C cubed. Okay, there's a pair of C's. So they come out C cubed. Then you have 3D's, right? This is where this gets a little messy. So D cubed goes D, 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 right? I need how many in a group? I need 2 in a group. So there's my 2D's. They come out as 1. And then I have how many left over? 1. So where this gets a little confusing is whenever your variables come out with the same index as what they're left in, or same exponent. Okay? But if you split them off like that, it makes them make sense. Okay? So then the answer to 3 is 2 C cubed D square root 3D. Alright, number 4. Cube root of 27 is what? 3 and 9. When 9 goes how? 3 and 3. So see how I just made it a 3-leaf tree? Okay. They all come out as 1. Okay, so you got 1 3 out of there. Y to the 12th divided by 3, you get what? Y to the 4th evenly, so you're good. So Y to the 4th out. Z to the 7th divided by 3. What do you get? Z to the 2nd, right? Z squared goes Z to the 2nd. Z to the 2nd. Z to the 2nd, right? Because you need 3 of them. And then how many Z's am I left over? 1. There's your 3 Z squares. They come out as 1. And you're left with 1 little Z all along. So the answer to this guy is 3 Y to the 4th Z squared cube root of Z. Okay. Make sure that you make your index like different from an exponent. Make sure it's smaller in the crack of the radical. Okay, that way I know you know it's the index. Okay, makes sense? Like radical expressions. All right, so now we're going to move into the adding and subtracting portion of the show. And that means we need to make sure that they are like. If you are like with your radicals, it's like terms, then you have to have the same index and the same radicand, which is fancy talk for what? The radicand is the what?
Number of root.
Nope.
Number inside.
And number inside. The stuff inside the radical. Okay? So, for example, you don't have to write all those, but just watch, okay? 3b, or square root of 3b, and 4 square root of 3b. Those are like. 3b and the cube root of 3b. Same radicand, different index. Not like. Square root of 3b and square root of 2b. Same index, different radicand. Not like. Okay. So, whenever you add or subtract these guys, they have to have the same index and the same radicand. Okay? Now, to be quite honest, these problems don't mix indexes. Alright? They don't. They don't mix indexes. You'll never see a problem that's like 2 rad 3 plus 3 cube root of 3 plus 3 fourth root of 3. Nothing like that, ever. So you really don't have to worry about the index part. You need to make sure, though, that the radicand is the same. Okay?
So the first one doesn't really have an index?
It's an index of 2. If it's not there, it's 2.
Okay.
Okay?
So, okay, I understand.
The problem is, sometimes, they're not just going to give it to you outright. Nope. Yep. We actually have to subtract the square root of 98 minus 2 times the square root of 32. That's what we got to do. Okay. Now, as it sits, are those radicands the same? No. One's 98, one's 32. So at this point in the juncture, you can't do anything. Except for what? Factor tree that stuff. Okay. So 98. So now you got to factor tree 98. Okay. 98 is what? The factor tree. Anybody know? Well, it's even, so that means we know what goes into it. 2. Okay. 2 and 49. Oh, look at that. And 49 goes 7, 7. Look at that. So there's your pair of 7s. They get to come out. And the square root, and the 2 stays inside. So that's the square root of 98 factor tree. Minus, what's the square root of 32 factor tree? 8 and 4. Okay. 4 goes 2, 2. 8 goes 2, 4. And 4 goes 2, 2. Okay? You guys are making this hard. You know that? So now you circle your pairs, right? Because it's an index of 2. So there's a pair of 2s. There's a pair of 2s. Okay? So those pair of 2s together come out as a what? A 4. Okay? Because you both bring them out together as a 4, right? You might as well have made it just 4, 16 and 2. And the 16 would go as 4 and 4, right? Everybody good? Okay. Now, what's my number outside this radical then? It's 8. Why 8? Because you got to multiply that by that 2. Okay. There's a 2 already there. Times the 2's you bring out as a 4. Times the square root of the 2 that's left inside. Right there. See them? It's all multiplication, so you got to put them together. So then what is 2 times 4? 8. So 7 square root of 2 minus 8 square root of 2 gives you negative 1 square root 2. The end of radicals don't change when you add and subtract. Okay, remember that from yesteryear? So always try to look for your perfect squares, right? Especially when you're doing square roots, obviously. Okay, so 12 goes how? Factor tree. Factor tree. 4 and 3, right? Okay, so, yeah, come on, there we go. So 12 goes 4 and 3, 4 goes 2 and 2. These 2's come out as 1, right? And then you have to multiply it with that 5. Everybody see that? So then what's the first term going to become? 10 rad 3, good. All right. Next term, square root of 27, factor tree it. Goes 9 and 3, and 9 goes 3 and 3. There's your pair of 3's, and you got to multiply that with 2. So the second, let me move this down just a little bit. There we go. So the second term is going to become what? 6 rad 3 plus. All right. 128 goes how? Hey, man. Emily? How's it go? 8 rad 2. What's your factor tree? Uh-huh. 2 and 64. And 64 goes. Oh, go quicker. 8 and 8. Alright. And your pair of 8s, they come out right there. Okay. Minus 8 rad 2. Okay, so now what are your like terms? The rad 3. So 10 rad 3 plus 6 rad 3 gives you how many rad 3s? 16. Rad 3 minus 8 rad 2. That's your answer. What 4-letter F word am I thinking of right now? FOIL! Do it! Go! Okay, let me get set up here. So 4 rad 3 times 3 rad 2. Multiply the outside, so 4 times 3 gives you 12. Rad 3 times rad 2 gives you rad 6. Outsides together, insides together. Alrighty. Next up. 4 rad 3 times negative 6. So positive times negative is going to mean negative. What's 6 times 4? 24. Whoops. And the square root of 3. Let's see that. That was your outside, so now we move on to insides right there. So 5 rad 2 times 3 rad 2. So 5 times 3 gives me 15. Rad 2 times rad 2 gives me square root of 4. And now your last. So 5 rad 2 times negative 6. So positive times negative gives me negative. 6 times 5 gives me 30. Square root of 2. Okay, let me move this separate down just a little bit. There we go, perfect. Okay? Everybody good? Now, after you FOIL like this, it's very important to go through and check all of your radicals and see if anything simplifies. And if something simplifies inside a radical, you need to do it because you could potentially have to combine like terms after this. Okay? So, do you see any radical that should simplify? Nash? No? 6 goes 3 and 2, that's it. Which radical you see should simplify?
4.
The square root of 4. Okay? Because the square root of 4 is what? 2. So what does that term become then if we're going to multiply it by 2? 15 times the square root of 4. The square root of 4 becomes what? 2. So it becomes 15 times 2, which gives me 30. So 12 rad 6 minus 24 rad 3 plus 30 minus 30 square root of 2. And that's it, because there's no like terms amongst those. Okay? Seven rad 2 times 7 rad 2.
49 rad 4.
49 rad 4. Good. Next one. 7 rad 2 times, whoops, times a 3 rad 3. So 7 times 3 gives you 21 rad 6. Okay, next up. Negative 3 rad 3 times 7 rad 2. Negative 21 rad 6. And lastly, negative 3 rad 3 times a positive 3 rad 3.
Negative 9 times rad 3. 9, sorry.
Negative 9 rad 9.
Yeah.
Woo! Okay. What do you see? Hopefully you see two or three things. The middles cancel out. See that? 21 rad 6 minus 21 rad 6 gives you 0 rad 6, which is 0. Right? Okay. So you're left with 49 square root of 4 minus 9 square root of 9. What else do you notice? Those simplify, right? What's the square root of 4? 2. What's the square root of 9? 3. So 49 times 2 gives me 98. 9 times 3 gives me 27. 98 minus 27.
Oh.
You could turn an ugly FOILing problem into a number. Look at that, okay? All right, your homework is page 419, 1 through 12. Skip 3 and 4.